Welcome to Probabilistic Programming Primer. We're going to talk about something different here. We're going to talk about Pyro. And those of you who do not know, Pyro is a probabilistic programming framework from Uber AI, and it's at a lower level of abstraction than PyMC3, so it's a little bit harder in some sense to get started. So I'm not an expert in Pyro, so I'm going to live code an example, kind of like basically from an example that is there. I'm going to sort of build that up step by step. So I'm going to help you on my journey. For those of you who don't know, Pyro is based on PyTorch, so it's the framework from Facebook. So let's get started. The first thing we're going to do is we're going to build up a toy dataset. So there's nothing here that's too complicated. This is just like your random vector that you're creating, your random integer weights. You're going to print it. You're doing matrix multiplication. You're creating a tensor. So like in PyMC3 with Theano, PyTorch uses tensors, and you're creating like a data set as well. This is a nice bit of defensive coding here. We're doing like an assertion. We're building a regression model, so it's a really simple neural network with one linear layer. We're going to call the size of the data this. We're going to put p equals 4. So that's from this part. So let's pull in the model part, and then we'll talk through it. So we're going to create like unit normal priors over the parameters, and you notice this torch.size aspect. We're going to do a bias for the location parameter, a bias for the scale, and you can see that it's just a case of like filling in the gaps here. And this here is a little bit unusual for me, so I don't actually know what this independent means. So let's look that up. Let's go to the docs, look at distributions. We're looking for normal, wraps, torch.distribution with distribution dot. Let's look at the source. So it seems that every distribution has some sort of independent aspect to it. But what's the independent represent? If anyone figures this out, they're more than welcome to tell me. Okay, so it just adds a conditionally independent aspect. My understanding, and I could be wrong, so feel free to write in or tell me off, is that this just makes the normal distribution independent, conditionally independent. And this means that we can use this pyro.ia range, but we can't use that unless we do this. So we do this other thing. We do a lift module parameters to random variable sample from the priors. This is this pyro.random module thing. We have quite a similar syntax here to PyMC3. We're running it over like a data frame of some description, and then we're calling sample. So it's not so hard right now, but like it's not quite as easy in my opinion. We're gonna pull out this guide. Yeah, so we have this sort of guide thing. So you can see that it has a few things in here. It has device. The reason it has device is that Pyro can run on GPUs. It has dtype for data type. We're registering learnable parameters in the same way that we would do this with any kind of like neural network. So we want to do things like guide mean weight. We want to do guide log scale bias. We have here Gaussian guide distributions. So let's look like a little bit into like what a guide is and why we need a guide. So let's look at the documentation for this example. Okay, alright. So in order to do inference, we're going to need a guide, and the guide is a parameterized family of distributions over WMB. Writing down a guide will proceed in close analogy to the construction of our model, with the key difference that the guide parameters need to be trainable. To do this, we register the guide parameters in the param store using pyro.pyram. So I'm actually going to put this in to our code so that we have it. So this is a specifically Pyro thing, and you see here that we have like registered learnable parameters, and this returns a regressor, right? This next bit, we're just returning an array of batch indices. So this is like quite a common thing if you've ever used like NumPy or any real like index-y kind of library, anything with like tensors or arrays. And let's like pull in these last two parts, and then we can run this kind of end to end. So the first thing we're going to do is we're going to have a look at this main thing. So you see that here that we clear our parameter score. Then we're going to build our linear data set. This here doesn't really matter because I'm not going to be running this on a GPU, but if you're running this on a GPU with CUDA, and CUDA is it's the thing from NVIDIA for running things on GPUs. It's a library or a framework. Well, you have to convert your tensors into CUDA friendly tensors. We perform inference, so we're calling Atom, and we're calling the Atom. We're going to change some of these things ourselves whenever we run this and see if we get any difference. We have Elbow, which is our evidence-based lower bound. Unfortunately, we don't have time to go into that. SVI is stochastic variational inference, so this is in the same way that you might use Monte Carlo sampling. So Markov chain Monte Carlo sampling. An alternative way to solve Bayesian models is to use variational inference. So we didn't have time to talk about that in our course, but we might do another section when we're talking a little bit more about variational inference. And that's just kind of running mini batch, shuffling data. For those of you who don't know mini batch is rather than training everything on all the data at the same time, you train in them mini batches of the data. So it's quite a common technique in modern day machine learning. And then we have our main argument. Let's see if we can source Python. Are we gonna run this one? What do we need to do to run this? This is where I took all the code from. I'm just gonna run this normally. Python Pyro. Okay, so we haven't installed Torch. So let's install Torch. We'll do pip install this. We're just gonna install Torch. Okay, let's run that again. Okay, and you can see how it runs. So we have our average loss, and our average loss is 0.9. After a while, it's 0.94. Let's just make sure that my actual example runs. So my example runs too, and you see that the loss goes down over epochs. You can also see that your weights change randomly each time you run it. So just to wrap up, to see what we talked about, we introduced a lot of material there, so I'm sorry if it was a bit overwhelming, but my point was just to show you what a Pyro example would look like. We introduced Pyro, which is from Uber AI. We did Bayesian regression. We want to learn a function of the form y equals wx plus b. We build a toy data set where we create random integer weights. We use random integer weights, so we built a data set to do linear regression on. We created a neural network with one linear layer. That's what we're going to use to learn on our data. And we introduced two things that are important in Pyro. We need a model. So we create a model which is very similar to how we would create it in PyMC3. We have to create a guide. And the guide is a parameterized family of distributions over W and B. The key difference is that the guide parameters need to be trainable. And then we run that all together with various inference algorithms and an optimizer. And this is really what we use to do inference in this case. So I'm just going to wrap that up right now. So thank you for listening. I hope you enjoyed this edition of Probabilistic Programming Primer. I'm going to continue to add material over the next couple of months, so don't be alarmed if you don't see anything. It's kind of like whenever I get time and inspiration. Thank you very much. Thank you for listening.